Welcome back. So in this video, we'll be looking at first the big functions in complex numbers, trigonometric and hyperbolic functions, okay? So let's look at ordinary trig functions. And how are they defined on the complex plane? Okay, so let's suppose we have the following two equations, right? So we'll have e to the ix. This equals to cosine x plus I times sine x, right, from Euler's identity. And we have e to the minus ix. This equals to cosine x minus I times sine x, right? Okay. So if I add the first and the second equation together, what I will get is 2 times e to the minus ix on the left-hand side. The I sine x's will cancel, and oh, I'm sorry. It's not right. So on the left, I'll have e to the ix plus e to the minus ix, excuse me. And then on the right, I'll have 2 times cosine of x. Okay. And then we can get a straight up definition of what cosine of x is. Cosine of x, in terms of complex numbers, this equals to e to the ix plus e to the minus ix over 2, right? If I subtract, on the other hand, the first and the second equations, right? What this is going to look like is e to the ix minus e to the minus ix. And on the right-hand side, the cosine of x terms will cancel. And I will get 2 times I times sine of x. So we can arrive at a definition of what sine of x is, right? Sine of x, if x is a complex number. So this is e to the ix minus e to the minus ix divided by 2I. Okay, so this is the other definition of the trig function sine of x. Okay, so we can use these to define the sine or cosine of a complex number, right? So let z be a complex number. Then sine of z, this equals to e to the iz minus e to the minus iz divided by 2I. And then cosine of z, this equals to e to the iz plus e to the minus iz over 2. Over 2. Okay. So those are a few things to take note on. And the various trig identities would work also, as you have seen in pre-calculus. So tangent of z is equals to sine of z divided by cosine of z, right? And then the reciprocal functions, cosecant of z, this equals to 1 over sine of z, right? Secant of z, right? This is equal to 1 over cosine of z, right? And then cotangent. Cosine of z divided by sine of z. Okay. And cosine of z divided by sine of z. Okay, so not a surprise there. So for example, compute the following numbers. sine of 2 plus I. With this one, for example. Okay, so sine of 2 plus I. So by definition, this equals to e to the I times 2 plus I minus e to the minus I times 2 plus I divided by 2I. So this equals to e to the minus 1 plus 2I, okay, minus e to the 1 minus 2I over 2I. And so this equals to e to the minus 1 times e to the 2I minus e to the first power times e to the minus 2I over 2 times I. And this equals to 1 over e cosine of 2 plus I times sine 2 minus e times cosine of 2 minus I times sine 2 over 2I. Okay. So this is equal to 1 over e cosine of 2, and figuring out the real components of minus e cosine 2, and then the imaginary component. So 1 over e times sine 2 plus e times sine 2 over 2I. Okay. So I will have so 1/2 2 e sine 2 minus 1/2 times okay. So that would be that complex number, right? Yeah. And I want you to work on your own computing this number. If you have questions on figuring out what this number is, please let me know. Okay. Pi minus 2I. But really, you're just using sine pi minus pi minus 2I divided by cosine of pi minus 2I, right? The 2's will cancel, and so you'll have so e to the I times pi minus 2I I 2I I minus 2I 2I. And then you're just going to write out the definition of the exponential function, and you should be able to get to the right answer, right? So, yeah, so hopefully this should give you a head start on solving that problem. Okay. Then we're going to look at some trig equations. Why not? So if I have this example, I want you to think about this one. Solve for z where sine of z is 5. Okay. pause the video and I want you to think about this for a bit, okay? Okay, so I assume you worked on this example. So we want to use the definition of what sine of z is, right? So sine of z, this is just e to the iz minus e to the negative iz over 2I, and this equals to 5, right? Multiply both sides by 2I, and you'll get, so multiply both sides by 2I, right? And so the left-hand side, this is just e to the iz minus e to the negative iz. This equals to 10I. And we want to multiply both sides of this equation by e to the iz. Okay, let's see what happens. If we do that, if we distribute e to the iz into these quantities here, so we'll have e to the e to the 2iz. So you add the exponents, that's a -1. And then this equals to 10I e to the iz. Okay. So actually we'll have, so if we add this quantity to both sides, we'll have e to the 2iz minus 10I times e to the iz minus 1 equals 0, right? Equals to 0. So if we apply this substitution of u is e to the iz, we'll have this quadratic equation in u's. So it'll be u squared minus 10I times u minus 1 is 0. Okay. All right. So, and then we're going to use the quadratic formula in the complex plane. So u is equal to 10 times I plus or minus square root of minus 10I squared minus 4 times minus 1 times c. A is 1, so the A is 1 plus 0I. C is -1 over 2 times A, right? So this equals to 10 times I plus or minus the square root of, so I squared is -1, so this is -100 plus 90, I'm sorry, shoot. -100 plus 4 over 2. And so this equals to 10I plus or minus root 96 times I over 2. Okay. And so u is equal to either 5I plus or minus 2 times root 6I. Okay. So we'll have two distinct values for u. So u is equal to 5 plus, shoot. Okay. All right. But we need to solve for z, right? U is e to the iz. So this means e to the iz equals to 5 plus times I. This is times I here. 2 root 6 times I. And then e to the iz, this equals to 5 minus 2 root 6 times I. And if we take the principal logarithm of both sides, right? Of these guys. So we'll have I times Z. This would equal to the natural log of 5 plus 2 root 6 times I. And then I times Z is equal to capital 2 root 6 times I there. Okay, so I times Z here is equal to, so we'll have the same radius. So log base E of, so the square root of 5 squared plus 2 root 6 squared. 25 plus 24, that's 49. 49, and then plus I times the inverse tangent of 2 root 6 over 5. Okay, so we want this value to be minus up to minus pi and pi, right? And the other way is oh, okay, I made a mistake. It's 5 plus 2 root 6 I. The real component is 0. Okay, so this would have an argument of pi over 2, right? It's 5 plus 2 root 6 times I. So it's a point that's in this quadrantial angle, right? So its argument is pi over 2. Okay, so this is pi over 2. Okay, and 5 minus 2 root 6, I believe that's bigger than 5. So in other words, this is positive. It's bigger than 0. So um, let me actually double check that. So 5 minus. Yeah, so that is positive, right? So it's in the pi over 2 axis, right? So it will be at the same point here, right? So this will yield the same value. Okay. Log base E of, in this case, so this will be 49 and then plus I times pi over 2. Okay. So these would be the same number. Okay. And then Z is just, so this is minus pi over 2, minus log base E of 49 times I. So 7 squared. So you can just write this guy as the second quantity as 2 times log base E of 7. Okay. So in other words, right, this is just your result here. Okay. So hopefully that made sense. And how you would solve trig equations. There is a specific definitions on how to take the modulus and the modulus and the argument of the complex number of sine of z, I guess. But really what I want to discuss more importantly is the mapping. The mapping of the trig functions. Okay, So I'm going to use sine of z in this example, but this process will be the same for finding the mappings for cosine of z. So sine of z by definition is e to the iz minus e to the minus iz divided by 2I, right? And then if z equals to x plus iy, our goal is to figure out the real and imaginary components for sine of z, right? So sine of x plus iy. Okay, so this is equal to e to the I times x plus iy minus e to the minus I times x plus iy divided by 2I, right? Okay, and so this quantity would equal to, okay, so this is e to the I x times e to the minus y, and then we'll have a minus e to the minus ix times e to the y over 2I. Okay, so this quantity would equal to following. So we'll have e to the minus y, e to the ix, this is just cosine of x plus I times sine of x. Okay, that's quantity number one. Okay. Quantity number two, right? This would be, so this is minus e to the y times cosine of x minus I times sine x over 2I. Okay. So now what I'm going to do here is to gather the real and imaginary components of the numerator. Okay, so that's what I'm going to do here. So with the real component, what that is going to look like is, so I'll have e to the minus y cosine x minus e to the y, excuse me, e to the y cosine x over 2I, okay? And I'll have the imaginary components next, plus I times e to the minus y times sine of x plus e to the y sine x over 2I. Okay. It's the real and imaginary components together. Okay. So, all right, I'm going to focus on the this quantity here first. This will be the imaginary component. And this component right here is the real component, since the i's will cancel. Okay, so the i's cancel. This will become the real component. And this right here is the imaginary component. Okay. So, no, actually, let's look at the real part first. The real component, right? This will be, so if I factor out a sine of x, I'm going to write out like this. So if I factor out a sine of x, so we will have e to the y plus e to the minus y over 2. Okay. And then, so this is plus I times the imaginary component. So I'll have a cosine of x that's factored. And if I divide by the conjugate, minus I in this case, So I will get e to the y minus e to the minus y over 2. Okay. So what we just did here is we wrote out sine of z in terms of the real and imaginary components. I don't know if you recognize this quantity here. This is hyperbolic cosine of y. And this quantity right here, this indicates hyperbolic sine. We'll talk about hyperbolic trig functions later. But in the real sense, in the real numbers, those how you would define those two functions. So we can actually express this as sine of x hyperbolic cosine of y plus I times regular cosine of x times hyperbolic sine of y. Okay. So this is sine of z. This is how you express the number sine of z in this case. So for sine of z, the real component is sine of x times hyperbolic cosine y. And then v is equal to cosine of x times hyperbolic sine of y. It's important to take note of these equations for u and v. Okay. Also, you can work this on your own, but you can express cosine of z in terms of the real and imaginary components. So, so cosine of z, remember, it's just e to the iz plus e to the minus iz over 2, right? And if you work this out in terms of the real and imaginary components, the real component should be cosine x times hyperbolic cosine of y. V is equal to minus sine of x hyperbolic sine y. So it's important to take note of these equations for u and v here as well. Okay. So let's look at some so with that, let's look at the image of, let's say, sine of z, right? Sine of z. Okay. And in order to do this, we're going to take note of a very famous trig identity for hyperbolic trig functions, and it's this. Hyperbolic cosine squared of x minus hyperbolic sine squared of x is 1. Okay. So this reflects off the unit hyperbola. The unit hyperbola, x squared minus y squared is 1. That's how the hyperbolic functions came about, right? So you're looking at the unit hyperbola this time. Okay. So we know that sine of x and cosine of x are periodic, right? And so shoot. So we can pick any range starting at, let's say, x naught and end at x naught plus 2 pi radians, right? And so this length is 2 pi, right? And so yeah, so in this case, we want to define the range of x which x is in between minus pi over 2 and then pi over 2, right? Minus pi over 2 and pi over 2. Okay. You'll see why we're not including minus pi over 2 here in a moment. So okay, so we have to look back on how we define the real components for and the imaginary components for sine of z are. And these are these equations here. Okay, so we had u equals to sine of x times hyperbolic cosine y, and then v is equal to cosine x hyperbolic sine y, right? So for this first set of images, we're going to look at the equation, the trig equation for the hyperbolic trig functions, right? So if we solve for hyperbolic cosine y and hyperbolic sine y, right, we'll just get hyperbolic cosine y equals to v divided by sine x, and then hyperbolic sine y is equal to, oh, shoot, this is u. That's u, and this is v over cosine of y, the cosine x, shoot, excuse me. Okay. Also, if you look at the domain for in the real numbers of these functions, hyperbolic cosine and hyperbolic sine, so hyperbolic sine, right, is this definition, e to the minus x over 2, and then hyperbolic cosine is equal to e to the x plus e to the minus x over 2. Okay, the domain is all the real numbers. E to the x and e to the minus x are never 0, right? So so in our so we want our range for x to be in this restriction, but y can be any real number. So y is any real number on the real number line. So on the z plane, so this is our z plane. Okay, so we're going to have this infinite vertical strip. It's defined vertically. So right, it's right in here. Okay. All right, so right in that strip. And what we want to do is we want to look at various images of the points inside that vertical strip. All right. So by using this hyperbolic trig identity, we'll have so hyperbolic cosine squared of y. So that equals to u over sine of x squared plus v over cosine of x squared equals, I should say, minus equals to 1. So therefore, we'll have u squared over sine squared of x minus v squared over cosine squared of x equals to 1. Okay. And if x is equal to some value a, right? Right, this is what it looks like. Okay. Now the only restrictions is where sine squared, where sine of a is 0, right? So we know that, so our range is minus pi over 2 to pi over 2. So we're not including those values. And also at 0, right? Cosine of 0 is 1 and sine of 0 is 0, right? So a can't be 0 for minus pi over 2 and pi over 2, okay? But nevertheless, if I were to pick x equals a, inside this strip. Okay, so here's x equals a here. What this looks like is, well, this is an equation for a hyperbola. So images of vertical lines, x equals a, would give us hyperbolas in the W plane. So here's what that looks like. So here is my W plane. So u squared minus v squared is 1. And to figure out, so with hyperbolas, you're going to have asymptotes. And the asymptotes in this case are at v is equal to plus or minus the slope, which in this case is cosine A divided by sine A times u, right? So rise over run. So that's how you figure out the slope. And then we're at the center, and we're going to move sine A in the u direction and cosine A in the v direction. Cosine A here, and then sine A there. Okay, and so sine A goes over here, and then cosine of A is over here. Oh, shoot. I need to do a different color. Cosine A is over here, and then you can draw in your box. And then you can draw in your asymptotes. Okay, and oh shoot, okay. I'll label hyperbolas like this in that color. So hyperbolas are going to open like this, since the v is negative. So we're going to go this way. All right. So at x equals a, we're going to have hyperbolas going, spreading out this way, right? From the left and to the right. Okay. On the other hand, if I have a horizontal line along y equals b, let's say here, along y equals b. So if I look at y equals b, so that means x is in between minus pi over 2 and pi over 2. Well, we want to use the good old trig identity we know and love. So cosine squared x plus sine squared x is equal to 1, right? All right, so now we're going to solve the real and imaginary components of sine of z for sine of x and cosine of x respectively. So cosine x, well, this would equal to u squared divided by so I'm at sine x, and then hyperbolic cosine of b here, since y is b, and cosine b, and then cosine of x, this equals to v squared divided by hyperbolic sine squared of b. All right, so the good news is hyperbolic sine squared of b would not cause division by 0. So in other words, hyperbolic cosine and hyperbolic sine, their domain is all the real numbers. Okay. So there isn't any conflict for specific y values, right? That'll work for any y value. Okay. Nevertheless, if we use this identity, we will have so if I put in sine squared for each of these terms, so we would have, so u squared divided by hyperbolic cosine b plus v squared divided by hyperbolic sine squared b equals 1. And do you know what curves of that describe these equations here? Well, if you said ellipse, you were right. This is an equation of an ellipse in the W plane. An ellipse in the W plane. Okay. So if we look at, so I'm going to do these separately. So in the W plane, if y equals b, so here's the W plane. So really it's about which value is bigger than the other one, right? So I believe the cosine value is bigger. So you're gonna have ellipses that are elongated on the u-axis and it's short on the v-axis. Okay, but it really depends on the v number. Okay, on the b number, excuse me, not the v number. But regardless, you're gonna have ellipses. Okay, and it turns out, well, these curves represent orthogonal families, right? Orthogonal families. So they intersect, so the curves intersect at 90-degree angles. Okay. So the curves for the hyperbola will intersect the curves for an ellipse at 90 degrees. So that's what they're called, orthogonal families. So that's interesting about that. So and the last thing I want to talk about is the hyperbolic trig functions. Hyperbolic sine and cosine. And cosine. Okay. So these functions are analogous. Pretty sure I spelled that wrong. Are analogous to the hyperbolic sine functions in the real numbers. So they're defined the same way. Okay. In X. So hyperbolic sine of z, this equals to e to the z minus e to the minus z over 2. Okay. The second hyperbolic cosine is equal to e to the z plus e to the minus z over 2. Okay. And that's it for trig functions. Here's some problems for you to work with. And these are page 213, 2, 4, 8, 6, 8, 12, 16, 18, 20, 22, 24, 28, 32, 33. Those are problems for you to work with. Hope you enjoyed this video. So in the next video, we'll look at inverse trig functions and their corresponding maps. So And then much later on, we'll get into integration in the complex plane. So we're moving right along here, everybody. So hope you like this video. If you have questions, please let me know. And best of luck to all of you.